So let's continue. Remember, the idea here is you should do as much as possible yourself and just use these videos for hints and checking your answers. But if you're really stuck, you can follow along. So let's do the next one. We want to show, so now, what are we trying to show? We're trying to show that if I add up, let's go up to these guys. So 0, 0, 1, 3, 6, 10, 15. I add up this sequence of numbers, I get this sequence of numbers. Well, in other words, if I add up the sequence of numbers whose terms are given by n times n minus 1 over 2, then I get this guy, which is the next in this sequence, the n minus 1, n minus 2 over 6, over 3 factorial, in other words. Okay. Now we have to be a little careful, because remember, we're not taking this up to the nth term. We're going to stop at the n minus first term. And that's what's supposed to give us this sum. And remember, the reason I did that, which might have seemed a little weird, is that these are exactly the n choose r coefficients. And I wanted to go ahead and get those exactly on the nose. Okay, so here we are again. Okay, so we're talking about the sequence that goes 0, 0, 1, 3, and the nth term would be n minus 1 over 2, but we're going to stop just shy of that. Okay, and the claim is that that gives us this somewhat more complicated version of the formula with the 3 n's, the cubic. Okay, so I'm going to do it a little bit more quickly than the last time. Base case is done. We already did, it's in the table. Okay, you do have to remember to do the base case, but we did it. And whenever you're doing these things experimentally, sort of informal induction and guessing, you're going to have done a bunch of base cases. It's not going to be an issue. Okay, so the inductive step, we're going to assume that 0 plus 0 plus 1 plus 3 plus up to n minus 1, n minus 2 over 2 is equal to, ooh, and again, you know what, I keep forgetting, what we really want to show, and again, it's not a big deal if you don't clear the fractions, but I just think it's prettier. It makes the only tricky step easy. We're really going to show that 0 plus 0 plus, I'm going to multiply the whole thing by 6. 6 plus 18 plus dot 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 plus, and then if I multiply this last one by 6, it's going to be 3 times n minus 1 times n minus 2. And I just want to show that that's n minus 1, n minus 2. Okay, so that's just a slightly different version. Okay, so now I'm going to assume that that's true for some particular but unspecified k, not that it's true for all k all at once. And there's a 3 in front. Okay. I'm going to assume that that's true. Okay. And to show is that the next one, 0 plus 0, let's display that. Let me display that too. There we go. Okay, I don't know why I didn't display that. Okay, that if I take it one more step, and in taking it one more step, I'm not going to just hide the previous last step in the dot dot dots. I'm going to keep it there. And then what will be the next thing? The next version of this is where I do actually go up to k minus 1. And then this should be where everything is boosted up. One of the mistakes students make here is they think that the pk plus 1 statement, so this is, again, statement p of k, it's the assertion that that whole equality is a true equation. And then this one is p of k plus 1. One of the mistakes students often make is that they just kind of add 1 somewhere. They think, oh, it's about adding 1 to a number. And it's more deep than that. It's about looking at taking a variable, k, and everywhere that shows up, incrementing it by 1. So putting in a k plus 1 here, a k plus 1, then, but in the role of the k, when you put that in, k plus 1 minus 1 is just k. K plus 1 minus 2 is k minus 1. So every place a k shows up, it gets incremented by 1. Okay, and then over here, because it was a summation, what is the next case of the summation? It's exactly what we had before, and that's what we're going to use for the inductive step, plus the next version. And the next version, again, is where k minus 1 changes to a k minus 2 changes to a k minus 1. Okay. It can be confusing, but it's really, it can be helpful. I don't think I'll write it out, but it can be helpful if you just write it out for like when k equals 5 or something like that. What's the statement for k equals 5? What's the statement for k equals 6? And in our book, they do go through it that carefully because it can be really, really helpful. But I'm assuming we're a little bit past the basics of induction at this point. Okay, so that's what I want to show. Okay, so I'm just going to write that out again. I'm going to use copy and paste. Okay. I'm going to take the left-hand side of the equation and try to show it as the right-hand side. And the first thing I'm going to do is use the inductive hypothesis, which is, hey, I have a closed formula for that. I'm allowed to assume that this is k minus 1, k minus 2. Okay, plus 3, k minus 1. Hey, look, there's a common factor. Oops, not what I wanted to do. K minus 1. That was exactly not what I wanted to do. Sorry. Guys, it's getting pretty weird here. Okay, let me bring that back to the middle. So there's the k minus 1 factor. There's k minus 1. Okay, so that is just k times k minus 1 times what? K minus 2 plus 3. Boom. K minus 1, k plus 1, and we're done. That shows the inductive step. So we assumed it was true for k. We assumed P of k statement. We got P of k plus 1 statement. We know that the first few are true. We really just need one, but we know that the first like 8 are true. Okay, and so this is true for all positive integers, actually all non-negative integers, and to be honest, because we checked 0 too, by induction. Rockin'. Okay, in the next one, we'll go through the last two. This is going to be really similar, really similar. This should definitely be one you should do on your own, number 3. But I'll show it, and then number 4 to just bash out the whole general case.